Alright guys, well thanks for coming. Hope everything's going well. Just to remind you, we're going to have a definitions and theorems and propositions quiz on Wednesday. It's only going to be worth 10 points this time. I'm going to combine this one with the one, I'll have another one after the break, but it's only going to be like 5 minutes. So be real quick and short, but you should be working on your statements of the theorems and the definitions from 4.4, 4.5, 5.1, and 5.2. So that's on Wednesday. And then I posted some more problems for you for Friday already. Another assignment. Actually, one more problem from 5.2. And then 5.3, I'm going to do a very fast lecture on 5.3. So you might want to read. It's only like 1 page long. Well, 2 pages, I guess. So just a real fast lecture on Monday on 5.3. That's what I'm going to do. And then I'm going to start integration. I've decided I'm going to skip L'Hopital's rule, because really the only thing there that's, all of the problems are just evaluate the limits, and that's just Math 150A stuff. So I'm going to assume you guys know that and just skip that section and get straight into integration, because I would like to have as many classes as possible for integration. So that'll be good.
Are we going to be able to use L'Hopital's rule even though we don't go through the class?
Good question. I don't think it's going to be relevant. I don't see why you can't use it, but maybe I'll at least state the darn thing. But I don't think I'll go through the whole proof of it. So, yeah. I'll get back to you about that. I haven't thought that through totally. So yeah, what I wanted to do today was answer questions that you have about anything, including the homework that you're working on that's due on Monday. And then I brought these extra problems along as well, which are kind of in parallel with the homework, so it's more practice on the same stuff. And I kind of just want to go through it with you guys because I think they're good problems. But I do have the solutions posted, so if you have to leave early or you just want to look at my answers later, you certainly can do that. Or you can watch the video. So lots of ways to kind of get this stuff down. So how's the homework going? Does anybody want to ask me anything about that yet?
Are we allowed to assume or use the fact that polynomials are differentiable everywhere?
Yeah. Yeah, that's totally cool. Polynomials are differentiable everywhere, right? The reason for that is that basically as soon as you prove that x is differentiable everywhere, just f of x equals x, then because differentiation is preserved by products, scalar multiples, and addition, then any polynomial can be expressed in that way using those operations to the basic function f of x equals x. So as soon as you know that x itself is differentiable, which is easy to prove, then you know that every polynomial is differentiable. But you don't have to go explain all that. Yeah. And you can use the fact that the derivative of sine is cosine. That's actually on the sheet here. And you can use the fact that the derivative of the natural log of x is 1 over x. I think that comes up as well. So any of those derivatives that you already know from your earlier calculus experience, you're allowed to use those derivative rules unless it actually says in the question, use the definition of the derivative to come up with the formula. Hopefully that'll make it a little bit simpler. This assignment is focusing more now on the applications of derivatives, not so much computing them. So at this point, we're sort of taking a lot of the derivatives that we know for granted, and we're just using them to prove other things. Okay? So, other questions on any of the homework? Or we could start with the sheet and come back to the homework in a little bit, too. That's also, we can go back and forth. Has everybody made a good start on it anyway? I know some people who are done with it, so I know that it's, well, done with it. Of course, you also have to write it all up, right? You guys are probably to the point now where you just do it all on scratch paper first and then you have to write up a final copy. Yeah, somewhere along the line, I remember I learned that I can't just go straight to writing up my homework anymore. I have to solve it first on the side and then write it up. And it was somewhere around this class when I was a student that I think I learned that. So, okay, I tell you what. Let's just go ahead and dive into my problems then, and then that may prompt you questions that you guys might have on the assignment as well. Okay, so the first problem is the following. Let a be greater than 0 and prove that f of x equals 1 over x squared is uniformly continuous on the interval from a to infinity, right? So here's 0 and here's a, and we are looking at this ray basically. The book calls that a ray if it goes off to infinity or minus infinity. It's more or less an extended interval. And we just want to prove that this is uniformly continuous on that interval. Okay? Now, this should look somewhat familiar from previous homework, I think. So I think you guys already proved this in the last assignment that you got back. From the definition of uniform continuity. All right, so the definition of uniform continuity would be, for all epsilon greater than 0, there exists a delta such that as long as the absolute difference x minus y is less than delta, then absolute value of f of x minus f of y is less than epsilon. That should be a definition that everybody should know for the quiz next week in particular, the definition of uniform continuity on an interval. Or on a domain in general, actually. So basically, the way that you would have done that problem, this hopefully looks somewhat familiar, is you would have done backwards scratch work, right? And the scratch work would have looked like this. You don't need to write this down because you've probably already done it, right? Then you get a common denominator, so you're going to get x squared, y squared on the bottom, and then the top will be y squared minus x squared, which you can factor like that. So all of those steps are reversible, right? And then at some point what you have to do, well, one more reversible step is to sort of solve for, I guess I'll rewrite it as x minus y. So you get something that looks like this. And what you want to do is make this right-hand side smaller so that you can go backwards with it, right? So to make the fraction smaller, you either have to make the top of the fraction smaller, or you have to make the bottom of the fraction bigger, right? And the trick to that, if you remember from last week, was to make an assumption. And you can always do this with uniform continuity. You can assume that x is greater than or equal to y, because the two variables x and y are on equal footing with respect to the definition. That wasn't true for pointwise continuity. For regular continuity, you had an x and you had a c, and the c was fixed, and the x was sort of roaming around in some neighborhood of c. So that was not a scenario where you could just view them as interchangeable. But uniform continuity, remember that the delta is independent of any particular point c, so your two values, x and y, are they're both roaming around in this interval of width delta. Right? So you can make assumptions like this. I think there's a problem on this assignment where you need to do something like that, if I remember correctly. I can't remember. Maybe I'm thinking of something we're going to do over here in a minute. Anyway, so we'll come back to that. So basically, with this right-hand side and making this assumption, you can replace, what was it? You could replace the y with x, right? And that makes the denominator bigger. And then you've got 2x, and you can cancel one of the x's with the top. And then you can make the numerator smaller by replacing all the x's and y's with a, because x and y are over here somewhere, right? So you can replace everything with a on top. You remember doing that? Okay. So why am I asking you to do the problem again then? If we just did it last week in the homework from the definition, why would I be bringing it up again?
There's a simpler way.
There's a simpler way. Yes, there's a simpler way. You know what the simpler way is?
Show the derivative is bounded.
Right. Corollary 5.4 is going to be one that you want to always keep in mind. Very important corollary. It says if the derivative of a function is bounded on an interval, if the derivative is bounded on an interval, then the function is uniformly continuous on that interval. So what is the derivative of, so this is a faster solution. What is the derivative of 1 over x squared? Yep, just by, now that would actually be a nice one for me to ask you to prove from the definition. I won't do it right now, but you can just prove from the definition that the derivative of 1 over x squared is negative 2 over x cubed. If you want to practice that at home, it's probably a good thing to practice on. Okay, so that's the formula for the derivative. So then on the interval from a to infinity, we can look at the absolute value of the derivative. This is what you want to do, right? And of course, this is just going to be 2 over x cubed because everything, x is positive, and we can just drop the minus sign because it's got an absolute value on it. So is this bounded? Remember what Dom was suggesting is that we use the fact that if the derivative is bounded, then the function is uniformly continuous on the interval. So is this bounded on the interval that we were given? Yeah. By what, Matt? In other words, when you say bounded, we want to put something here. I need to make this fraction bigger, either by increasing the numerator or by decreasing the denominator. Yeah, again, if you look at where x is relative to a, you see that x is bigger. So the denominator is bigger here than it would be here, so I can replace this with 2 over a cubed. Why do I need to do that? Well, I need this to be a constant. This is now a constant, whereas 2 over x cubed is not a constant. Okay? So f prime is bounded on a to infinity. Really important you guys get in the habit of telling me where it's bounded or where it's uniformly continuous. Don't just leave that open because it might depend on the domain as to where it's bounded. Okay. For example, you couldn't get away with that if the a was, if this was like the open interval from 0 to infinity, you wouldn't be able to get away with that. So, okay. And in fact, on the open interval from 0 to infinity, this function is not uniformly continuous. Okay, it gets unboundedly steep. It gets as arbitrarily steep as you want as you get close to 0. So anyway, so the derivative is bounded, so by corollary, on this interval it is bounded, so by corollary 5.4, f is uniformly continuous on that same interval. Make sense? So it's a really nice corollary. Just take the derivative, convince me that it's bounded. There are some pitfalls though. Pitfall number 1 is, well, if you take the derivative and it doesn't appear to be bounded, or you have a hard time convincing, here we do have to do a little bit of work here. In this case it was pretty easy, but you will have to show me somehow that the derivative is bounded by taking its absolute value and putting it less than or equal to some constant. So that's something that's some work you still have to do. It's not just a totally free approach here. You still have to do some work. The second thing is that the converse of this statement is not true, and we're going to get to that in a moment. So just because a function is uniformly continuous on an interval doesn't mean that it has a bounded derivative on that interval. So I'm going to show you that in a second. So be careful not to take that conclusion too far. The third pitfall is that if your function isn't differentiable somewhere in your domain, then you can't use the corollary, right? Corollary says if the derivative is bounded, that there's an assumption there that the derivative exists, first of all. So if the derivative doesn't exist, then you can't use this corollary 5.4. Even if there's one point in the domain where the derivative, it might exist almost everywhere in the domain, but if there's even one point in the domain where the derivative doesn't exist, well, then you can't use the corollary. You'd have to change your domain to exclude that point and then show me that the derivative exists everywhere in that interval and was bounded there. So this one, of course, we know the derivative exists everywhere that it's defined, and that would be as long as x is not 0, which is perfectly fine for this interval. Right. Okay. Of course, a lot of times if the derivative doesn't exist somewhere, it could be because the function doesn't even exist there. If the function doesn't exist there, then obviously you're not going to be talking about the function being uniformly continuous somewhere that it doesn't exist. Right? It wouldn't make sense to say prove that this is uniformly continuous on some interval that straddles 0, because the function doesn't exist at 0, so that wouldn't even make sense, right? Okay, I'm doing a lot of talking here, not hearing a lot of feedback. Is everybody good with this? Okay. Maybe it's just I need to say these things just to emphasize them, but you guys already kind of know it. So, all right, let me show you that the converse of that corollary 5.4 is not true. So this is the second problem on the sheet, number 2. Basically, I'm going to give you this function, f of x equals the square root of x, and I'm going to give you the interval. I think I would just want to use the open interval. I is the open interval from 0 to infinity. Then there's two things here that we want to claim. The first claim is f is, in fact, uniformly continuous on I. And then the second claim is f is not, well, I should say f does not have bounded derivative on I. So thus, the converse of corollary 5.4 fails. Okay. This is a nice example to show that. F of x equals the square root of x. Now, of course, we know that the graph goes something like that. Okay, we're looking at the open interval from 0 to infinity. Which claim do you want me to work on first? I honestly don't care.
Claim 1.
All right, go in order. Claim 1 turns out to be the hard part. We'll just do the hard part first, and then the second claim will be much simpler. Okay, the reason that the first one is kind of difficult is, well, you try to do your backwards scratch work. I mean, basically, you've got to prove this from the definition, right? Because, well, we don't have, what other approaches do we have to prove uniform continuity on an interval? We have the definition. We have if the function has bounded derivative on the interval, but we already are looking ahead to claim 2 and saying that's not going to work. Okay, and what else do we have? Well, we have this, we can think about doing a sequence approach, but sequences are always used to disprove uniform continuity, so that's not really going to be helpful. So really, it's the definition is what we got. Okay. Well, there's a few other things. If we know that our function is continuous and it's a closed interval, then it's uniformly continuous on that closed interval, right? That was one of our theorems. But again, we don't have a closed interval here. So we don't really have a whole lot of other options. It's good to keep reviewing in your mind what our options are, because you're going to see problems where you're going to have one of those other options might be a good way to go. But in this case, there really isn't another approach to use. You really have to do this one from the definition. And it's actually a little bit tricky. I went online, I Googled square root of x is uniformly continuous on this interval. And there are lots of discussion boards about it. This is not something that's a simple little problem. So let me show you why. If you want to do it from definition, you're going to do epsilon delta, right? And you're going to do backwards scratch work. So if you look at backwards scratch work with me for a second, right? That's what you want. Basically you want to get radical x minus radical y less than epsilon. And you need to think about getting x minus y into it, right? Because the x minus y is what is controlled by delta. One way to get the x minus y into it is to multiply radical x minus radical y by radical x plus radical y. And I can do that on top as long as I also do it on the bottom. So if you're writing this down, just be forewarned that we're going to be erasing this in a minute. Okay. But anyway, that's what we have. Does everybody see how I did that? I basically view x minus y as a difference of squares. It's radical x minus radical y times radical x plus radical y, and after canceling, it reduces back to this. Okay, so this is the normal way we would do this then, is we would just solve this for x minus y here. And we would get this, and we would say, well, I can't let delta equal that because it's not a constant. So what I need to do is I need to make this bigger. I'm sorry, make it smaller. Make it smaller. But on this interval, making it smaller means you're going to make it 0. That's the only thing you could do that would be guaranteed to be smaller than this. And if you make this equal to 0, then you've got the absolute value of x minus y less than 0, which isn't true ever. So, so this is not going to work very well. So there's another way to do this, but it's a little tricky. Okay. Now what you do is, so now I'm gonna. Does everybody understand why this is problematic? See the issue there? So let me start off this proof with the following note. If we assume, this is where I want to again use the fact that I can assume that x is greater than or equal to y. If I do that, then if I look at radical x minus radical y, and I don't need the absolute value bars on it anymore, I actually claim that that's less than or equal to the square root of x minus y. And if this turns out to be true, then I'm going to be in great shape because I can force this to be less than the square root of delta, right? Because x minus y will be less than delta. So I can just choose delta so that the square root of delta is the same as epsilon. So if you believe the expression in the box, then I'm going to be in good shape. Is everybody with me on this? To prove the expression in the box, I'm going to actually prove that the square of the left side is less than or equal to the square of the right side. So in other words, this boxed equation is equivalent to radical x minus radical y squared less than or equal to x minus y. I'm going to do that. What I'm hoping to do is do some steps here. It's almost like scratch work backwards again, and then we'll go forward from there. So if I square the left side, I'll get radical x squared is x, and radical y squared is y, and the middle term is minus 2 radical xy. And this is less than or equal to x minus y. What can I do with that? Just algebra. What algebra can I do? I'm not looking for anything hard here.
You can do the x's.
X's cancel, right? Okay, let's just do that.
Y.
And then what?
Move the y.
Okay, move this y over here, so I get 2y. Then let me move this 2 radical xy to the other side. 2 radical xy,
Divided by 2.
divided by 2, and you've got a radical y on both sides that you can cancel. So that'll leave me with just radical y on this side and radical x on that side. And this is true if you started with this assumption here. So basically, if x is greater than or equal to y, then radical x will be greater than or equal to radical y, and I can now go backwards through each of these steps and get to here. So this box is true. Agreed? It's a little tricky though. But once you have that, you can think of that almost like a lemma. Sort of establish that first, then you're ready to do, then we can come back over here and give a very short proof that's based on that. So, let epsilon greater than 0 be given. So Jason, based on everything we've talked about over there, what delta would you want to choose?
Not sure.
Okay. Where do we see it on the board over here?
The top.
Right here, yeah?
Oh, epsilon squared.
There you go. Yeah, I want delta to equal epsilon squared. Exactly. Kind of a weird choice of delta. We haven't really done that very often. But that's what we're going to do. So then, if the absolute value of x minus y is less than delta, and x is greater than or equal to y is greater than 0, so I'm going to make sure x and y are in my domain, and we're going to just, without loss of generality, assume that x is greater than or equal to y, then basically the absolute value of f of x minus f of y, which is just radical x minus radical y, will be less than or equal to radical x minus y, which is less than radical delta, which is epsilon. So basically you just go present it all in one chain of inequalities now. So you don't actually have to retrace scratch work. We just simply, this is the step where we use the note that I put down on the other side to sort of justify that part. Does that make sense? So this is the hard part, claim number 1. F is uniformly continuous on the open interval 0 to infinity. People good with that? All right. What about the second claim? I guess we can talk about that next. Second claim is f does not have a bounded derivative on the same interval. Someone, do you have a suggestion how to tackle f not having a bounded derivative? Ulysses, how about you? I want to show that it doesn't have a bounded derivative. Does it have a derivative at all? Okay, so it does have a derivative, then maybe it would be helpful to figure out what it is. If we want to show it's not bounded, it would be nice. We don't know what it is yet, so maybe we should figure out what it is and then look at it. What is the derivative of square root of x? Okay, f prime of x is 1 over 2 radical x, right? Just by the power rule. That would be another one to practice proving from definition. Get a little practice on square roots. It's not hard. Okay, so this is a nice one to practice. Okay, so that's the derivative, and we're looking at the interval from 0 to infinity like that. So is this a bounded expression? Is there a maximum value that this takes on over this interval? No, definitely not. As x approaches 0, for x's that are very close to 0,